This video is a review about slope fields and separable differential equations. Problem number 1. Sketch the slope field. On the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. dy dx equals negative 2x over y. At the point negative 1, 2, the slope equals 1. So we should have a rising slope at a 45-degree angle. At the point 0, 2, the slope is 0, so we should see a horizontal slope. At the point 1, 2, the slope equals 1, so we should see a decreasing slope at a 45-degree angle. Other than the point 0, 0, whenever the x-coordinate is 0, the numerator will be 0, which makes the overall value of the slope equal to 0. So we should have horizontal slopes all along the y-axis, except for at the origin. I meant to put arrows here, not equal signs. At the point negative 1, 1, the slope is 2, so you should draw an increasing slope that is steeper than a 45-degree angle. So this one should look steeper than this one. At the point 1, 1, the slope is negative 2. So we should see a decreasing slope that is steeper than a 45-degree angle. The slope of this one should look steeper than this one. At the point negative 1, 1, the slope is negative 2. So we should see a slope that is decreasing and steeper than a 45-degree angle. These two should look the same. At the point 1, 1, the slope is positive 2. So we should see an increasing slope steeper than a 45-degree angle. These two should look the same. I think I accidentally put equal signs on the last couple of problems. These should be arrows. Anyway, at the point negative 1, negative 2, the slope is negative 1. So we should see a decreasing slope at a 45-degree angle. This should look the same as this one. At the point 1, negative 2, the slope equals 1. So we should see an increasing slope at a 45-degree angle. This one should look less steep than this one. Number 2. The slope field for a certain differential equation is shown above. Which of the following could be a solution to the differential equation with the initial condition y at 0 is equal to 1? Here's the point 0, 1, the initial condition. Let's draw a solution through that point according to the slope field. Given the initial condition 0, 1, the solution to the differential equation would look something like this. We can eliminate b, c, and d pretty quickly, so I'm going to address those first. Y equals 1 minus x squared might better be written as y equals negative x squared plus 1. In this form, it's easy to see that we are talking about an upside-down parabola with the vertex shifted up 1. So this is clearly not a parabola, so that's not a match. We know that y equals e to the x is an exponential growth curve, so this would look something like this. Definitely not a match. Option D is the positive side of the equation x squared plus y squared equals 1, where they have just solved for y. Hopefully you recognize this as the equation of a circle. So this is a semicircle. Clearly this is not a semicircle, so no match. Let's take a closer look at the cosine function. We know that cosine looks like this. So maybe that's what's happening. It is sort of dropping as we go to the right, just like cosine does. The reason why I know this is not cosine is because look at the bottom line here where we have a string of horizontal slopes on the slope field. When you see this, you are looking at a horizontal asymptote. And cosine does not have a horizontal asymptote. Also, notice that cosine has a value of negative 1 at pi, which is approximately 3.14. And then cosine has a value of 0 at pi over 2, which is approximately 1.57. So compare that to the graph. at about 1.5-ish, the cosine graph should be crossing the x-axis, so somewhere in between 1 and 2. Looking at our solution that we have drawn, it is nowhere near crossing the x-axis between 1 and 2. So this could not be the cosine graph. That just leaves the rational function y equals 1 over 1 plus x squared. Notice that the value of this expression could never be 0 or negative, so it makes sense that the x-axis is a horizontal asymptote. The answer is E. Number 3. The slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? So looking at the slope field, the solutions are all doing something basically like this. And if you notice that close to the y-axis, the slopes are starting to become vertical. It appears that the y-axis is a vertical asymptote. Y equals x squared looks like this, not a match. Y equals e to the x looks like this, again, not a match. Y equals e to the negative x is a reflection of the previous one over the y-axis, so it would look like this. Nope. Cosine x looks like this. That's not what's happening. The solution is E. We know that natural log x looks like this, which is a perfect match. Number 4, Part A. On the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. At the point -1, 3, the slope is 2. So you should draw an increasing slope that is steeper than a 45-degree angle. The point +1, 3 has the exact same slope, so it should look the same. At the point 0, 3, the slope is 0, so we should see a horizontal segment. And in fact, all of the points that have an x value of 0 will have a slope of 0. At the point -1, 2, the slope is 1, so we should see an increasing slope at a 45-degree angle. This should look not as steep as this one. At the point +1, 2, the slope is also +1, so these should look the same. At -1, 1, the slope is 0, so we should have a horizontal segment here. At +1, 1, same deal. At -1, 0 and +1, 0, the slope is -1. So in both cases, we should have a decreasing slope at a 45-degree angle. The steepness should match these purple segments, but obviously in the opposite direction. Part B. While the slope field in Part A is drawn at only 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. If the slopes are positive, that means that dy dx is greater than 0. So let's set up this inequality. Under what circumstances will this expression be greater than 0? So first of all, x cannot equal 0. If x is 0, then that's going to wipe out this entire expression, and you're going to get 0. That's no good. We need it to be greater than 0. So let's make a note. X cannot equal 0. Other than that, all right, so let's assume that x is not 0. What else does it take for this expression to be greater than 0? Well, if x is not equal to 0, then this first factor will always be positive, no matter what. Even if x is, say, -3, you square it, it's a +9. So this will always be positive. So that just leaves the y-1 factor. If y-1 is also positive, then you have a positive times a positive. That's greater than 0. If y-1 is negative, Then you have a positive times a negative. That's less than 0. So we need two things to happen. We need x to not equal 0, and we need y minus 1 to be greater than 0. That has to be positive. But y minus 1 greater than 0, if you add 1 to both sides, it gives you y is greater than 1. These are the same. We can say something like this. The slopes will be positive at all points where x is not equal to 0 and y is greater than 1. Look back at the slope field for a little confirmation. Look at the slopes where the y value is greater than 1. See how we have the positive slopes here? As long as x is not 0, we have positive slopes above the line y equals 1. Number 5. Consider the solution of the differential equation dy dx equals 2x minus y, with initial condition y at 0 equals 1. Use a tangent line at 0, 1 to approximate y at 0.2. When they ask us to find the equation of a tangent line, we always use point-slope form. So all we need is a point and the slope. And they already gave us a point, the point of tangency, which is 0, 1. So all we really need is the slope. We can use the first derivative to find the slope. All we have to do is evaluate the first derivative at the point 0, 1. So in this case, that'll be 2 times 0 minus 1, which equals -1. So that's the slope. Now that we have a point and the slope, we can easily write the equation. It'll be y minus y is equal to the slope times x minus x. We don't need the minus 0, so I'm just going to erase that. So we really just have this. So in order to use this to approximate y at 0.2, it'll be easiest if we get y by itself. So let's add 1 to both sides. We get y is equal to -x plus 1. We can use the tangent line equation to approximate the value of y at 0.2. Y at 0.2 is approximately equal to -0.2 plus 1. In other words, y at 0.2 is approximately equal to 0.8. Number 6. Verify that y equals x to the third power natural log x is a solution to the differential equation x y prime minus 3y equals x to the third power. To see if y equals x to the third power natural log x is a solution to this differential equation, we need to plug in an expression for y and y prime and see if we get a true statement. Obviously, we have an expression for y right here. We need to find an expression for y prime so we can plug that in as well. This is a product, so we will have to use the product rule. Taking the derivative of the first factor, I have 3x squared. I'm going to leave the second factor alone, natural log x, and I put a plus. Second time through, I leave the first factor alone, x to the third power. And I take the derivative of the second factor, which is 1 over x. So this is y prime. Now let's plug in y prime right here, and let's plug in y right here. I'm setting up for it. You see I have x times x prime minus 3 times y equals x to the third power. So I've written x times, and I've left space for y prime, minus 3 times, and here is the space for y, equals x to the third power. So as you can see, I plugged in my expression for y right here, and I plugged in my expression for y prime right here. The only change I made is that x to the third power times 1 over x simplifies to x squared. The x in the denominator cancels out one of the x's. Let's go ahead and do the distributive property with this x. And these parentheses are no longer needed. I'm noticing that the first term, 3x to the third power natural log x, is the exact opposite of the third term, negative 3x to the third power natural log x. So these will cancel each other out, and we are left with x to the third power equals x to the third power. So it checks out. Number 7, verify y equals 4 cosine 2x plus 6 sine 2x is a solution to y double prime plus 4y equals 0. To verify that this is a solution, we need to substitute an expression for y, which we have, and also an expression for y double prime, which we don't have yet. And we need to verify that the sum equals 0. But first, we need to find y double prime. In order to get y double prime, we first need to find y prime. So let's take the derivative term by term. I'm going to just bring down the 4. The derivative of cosine is negative sine. So I'm going to put negative sine 2x. But because this is not just an x, I need to do the chain rule and multiply by the derivative of the inner function, which is 2. Moving on, I'm going to bring down the 6. The derivative of sine is cosine, so I will write cosine of 2x. And again, because this is not a plain x, I need to do the chain rule and multiply by the derivative of 2x, which is 2. Simplifying a tiny bit, I have negative 4 times 2, which is negative 8. So negative 8 sine 2x. And I have 6 times 2, which is 12. 12 cosine 2x. This is y prime. Now I need to find y double prime. Let's bring down that negative 8. The derivative of sine is cosine. So cosine 2x. Chain rule, so times 2. And then I'm going to bring down this 12. The derivative of cosine, the derivative of cosine is negative sine. Chain rule, multiply by 2. Simplify a little bit. 2 times negative 8 is negative 16. So negative 16 cosine 2x minus 2 times 12 is 24 sine 2x. So this is the second derivative. I am going to substitute that right here. Meanwhile, this is y. I'm going to substitute that right here. So if we start with y double prime plus 4y equals 0, and we substitute this purple stuff for y double prime, and this blue stuff for y, then we have this equation. Does it equal 0? If you distribute the 4 across the parentheses, we get positive 16 cosine 2x plus 24 sine 2x. This is the exact opposite of the two terms that you see here in purple. So everything cancels out, and we get 0 equals 0. So it checks out. We just verified it. Number 8, find the general solution to the differential equation. That means turning dy dx into a plain y. And the general solution means we get to leave the plus c in the answer. This is a separable differential equation. So let's try to get all of the y factors on the left and all of the x factors on the right. The first step will be to multiply both sides by dx to get the dx over here. So that will leave us with dy is equal to x squared y dx. I would like to get this little y right here over here on the left. So to accomplish that, let us divide both sides by y. So that will give me 1 over y dy is equal to x squared dx. Now that I have all of the y's on the left and the x's on the right, I can integrate both sides of the equation. This first one is a memorized rule. The integral of 1 over y is the natural log of the absolute value of y plus c, but I will save the plus c for the right-hand side of the equation. For the x squared, it will become x to the third power times 1/3. You divide by the new exponent, plus c. So guess what? This is a general solution to the differential equation. However, sometimes they will ask us to write our answer in the form y equals f of x. So let's practice getting y by itself. I can get rid of the natural log by exponentiating both sides of the equation. In other words, I could drop a base e on both sides of the equation like this. Base e and natural log are inverse functions which cancel each other out. So that will leave me with the absolute value of y equals all of this. Rather than copy this down the way it is, I would like to split this apart using a property of exponents. Remember that if I have e to the n power times e to the p power, that would give me e to the n plus p power. When you multiply like bases, you add the exponents. But also remember that this process is reversible. If I have e to the n plus p power, I can split this up as a product and write it as e to the n power times e to the p power. And this is what I'm going to do right now. I'm going to take e, and I have this sum, and I'm going to split it apart as a product. So I'm going to write it as e to the 1/3 x cubed times e to the c. The reason why I did that is because e is a constant and c is a constant. So e to the c power is just another constant. So I am going to call this d on the next step. To bring the y out of the absolute value, all you have to do is put a plus or minus on the other side of the equation. It's a little bit like when you take the square root of both sides of an equation. So we have y equals plus or minus, and I will go ahead and put my new d in the front, and so I'll have plus or minus d times e to the 1/3 x cubed. And this is the form you are more likely to see as an option on a multiple choice question.